Welcome to this explainer. Today, we are popping the hood on large language models. We aren't going to treat them as some abstract, untouchable math, but rather as highly solvable software engineering problems. If you've ever wanted to truly understand what makes these massive models tick, there is no better way than looking at the raw code. Think of this as a masterclass designed specifically for the software engineering student's mindset. Let's get into it. Here is our roadmap. We are looking at debugging custom architectures, tackling the KV cache bottleneck, upgrading attention mechanisms, plumbing the agentic harness, and finally, mapping out your LLM mastery learning path. To anchor our mindset as developers today, we're adopting a core philosophy directly from our source material: working code doesn't lie. Research papers and blog posts can be incredibly vague, right? They leave out crucial details. But if you actually code a custom architecture, compare it to a reference implementation, and those outputs match perfectly, well then you absolutely know you've built it right. It's the ultimate verification. Section 1, Debugging Custom Architectures, the Easter egg hunt of weights and norms. So imagine you're coding an LLM from scratch in Python, relying on PyTorch's C++ and CUDA bindings to do the heavy lifting. You're porting over a custom architecture to mimic a model like Gemma 3. You load your weights, prompt it with a simple English question, and bam. The screen just fills with complete nonsensical gibberish in a foreign language. It's literally every developer's nightmare. Just a single coding error or one missed config detail can completely break the model. But hey, don't panic. When you get that gobbledygook, you just apply a systematic debugging process. First, read the config.json and the technical report. Update your architecture sketches and modify your code top to bottom. Then, feed in some random weights and run basic text generation. The real secret weapon here: do a layer-by-layer comparison with a trusted reference library. And a pro tip for you, just test 2 transformer blocks instead of all 18. It saves a ton of time while you hunt for the exact layer where your tensor values decide to diverge. And that brings us to a really fascinating bug fix during this whole Easter egg hunt. When comparing the tensor outputs, the very first divergence pops up right at the input layer norm. A regular RMS norm multiplies by a learnable parameter, usually called gamma, that starts at 1.0. But the Gemma RMS norm, it actually tweaks the formula. It multiplies by 1.0 plus s, where s is centered at exactly 0. Now, why does that matter? Well, these zero-centered parameters are a brilliant, deliberate engineering choice. By keeping that learnable parameter centered at 0 instead of offset from it, it makes it significantly easier for optimizers like Adam to actually stabilize the model training. This right here is exactly why building from scratch is the best teacher. You would totally miss under-the-hood stability tricks like this if you only ever used high-level wrappers. Section 2. The KV cache bottleneck. Finding the engine's memory limit. 52 gigabytes. Think about that number for a second. That is the staggering amount of RAM required just to store keys and values across all layers for certain regular attention models running 128,000 token context. 52 gigs is way more than most high-end consumer GPUs even have. That's a guaranteed out-of-memory crash. It is a massive physical hardware limit. To really grasp why this happens, we have to look at the KV cache. During inference, instead of recomputing past queries, keys, and values for every single new token, the model stores those intermediate computations in memory. It's fantastic because it makes inference drastically faster. But as we push for longer sequence lengths, especially for reasoning models and agentic harnesses, this cache footprint just aggressively balloons. Slashing this massive memory footprint becomes our absolute primary engineering bottleneck. Which leads us perfectly to Section 3, Upgrading Attention Mechanisms, re-engineering the transmission. If the standard engine is eating up too much memory, we have to radically change how the transmission works. Standard multi-head attention requires one query, one key, and one value computation per head. It is very thorough, but it is super expensive. Enter grouped query attention. This acts as a highly effective workaround where a single key and value representation is shared across a group of multiple queries. Yes, you take a very minor hit to response quality, but the engineering trade-off is absolutely worth it. Just look at this drop in memory pressure. By applying just 4 KV groups, we take that massive 52 gigabyte footprint and shrink it all the way down to a highly manageable 13 gigabytes. That is a 4x production just by cleverly sharing the state. This is exactly why modern models rely so heavily on grouped query attention today. But wait, We don't have to stop at just grouping queries. We can also restrict how far back the model actually looks. Sliding window attention restricts tokens so they can only attend to a fixed, deterministic bandwidth of past tokens. It's a hard-coded look-back distance. DeepSeek sparse attention, on the other hand, takes a much smarter approach. It dynamically learns the exact optimal subset of past tokens it should attend to during training, using a selection module. Both are just brilliant upgrades to dump unnecessary data from that KV cache. Of course, if you strictly limit the past context, you run the risk of losing crucial early information. So models elegantly combine these techniques, using a 5-to-1 ratio. You interleave 5 highly efficient sliding window layers for every 1 full global attention layer. This means every 6th layer gets to see the whole picture, ensuring that important early context isn't lost while keeping the overall memory pressure incredibly low. All right, Section 4, Plumbing the Agentic Harness, Plugging the Engine into a Self-Driving Car. Upgraded attention models are incredibly powerful, but the hottest trend is taking these highly efficient models and wrapping them inside a larger software ecosystem. We call this an agentic harness. Now, to be clear, this is fundamentally different from a simple chat UI. A chat UI just passes text back and forth. An agentic harness is the actual plumbing, a minimal Python software loop that gives your base LLM live repository context, short-term cache memory, and actual file permissions to execute autonomous tasks. Building a minimal agent means scripting this continuous, autonomous loop. First, the model inspects the live repository context. Next, it actively chooses a required tool. Then, it writes and tests new code files. And finally, it observes those results and iterates. You aren't just prompting anymore. You are orchestrating a completely autonomous software worker. And finally, Section 5, LLM Mastery Learning Path, from scratch to professional scale. So how do you map out your personal journey to master all of this? Well, you should follow a strict hierarchy. Start at the beginner level. Build pure PyTorch implementations from scratch. Do the hard work so you know the absolute truth of the code without any abstractions blinding you. Then graduate to the intermediate level by utilizing wrapper libraries like Hugging Face Transformers and TRL for speed. Finally, hit the expert level. Dive into the complex multi-GPU proprietary architectures of pro-level repos like Olmo or Megatron to see how the major labs scale what you built from scratch. So, as we wrap up this explainer, I'll leave you with this. What part of the LLM architecture are you going to try building from scratch first? Are you going to debug a custom RMS norm to see how zero centering affects stability? Or maybe try building a sliding window attention block from scratch to shrink that massive KV cache? The code base is out there waiting. Dive in, break it, fix it, and master it.